In this video, we'll recap from the last example and we'll learn from it. So in the last example, we looked at this linear system and showed that the solution set was a subspace, we found a basis, and we were able to describe it geometrically. All right, so let's look at this. The following proposition generalized the work done in the last example, proposition 7.5.2. The solution set of a There was something special about this, right? I had all zeros. And we've seen, in fact, that in the case where you don't have all zeros, where was that? Right here, if you have equals 3, then you wouldn't have a subspace because the first property would be wrong. And so we don't apply this to general linear system. We have a homogeneous one. The solution set of a homogeneous linear system in n variable is a subspace. All right, so let's prove this. It's not too hard. When using the techniques of chapter 3 to solve a homogeneous linear system, the solution set is written as, so first of all, the constants are zeros and stay zeroed throughout. So the constants are 0. And then we get S1, if we have K parameter, we get S1 times W1, SK times WK. And so if we simplify this, we don't actually need the 0, and what we get is simply a linear combination like this for all S1, SK in R. All right, so that's what we got here. And we do the same thing. That means the solution set is the span of these vectors, W1 through WK, and so it is a subspace. So when solving a homogeneous system, we get a set of generators, these right here, one for each free variable. Turns out this set of vectors that we get from solving is automatically linearly independent. So that extra step I did here, that was really quick, in fact, but that extra step will always work out, so you won't have to do it because I'll always have these 1 zeros here that are going to give me a leading one for each. So let's see this. To see this, consider a linear combination of my W's right here. To show that Sj needs to be 0, look at the row corresponding to the free variable. Its corresponding free variable, xi. So if xi corresponds to xj, then I'm going to have something like that. All zeros and a single one in Sj. Okay, that's what I had here. Y corresponded to S, and so I have a single 1 and then a 0. Perfect. So if I don't care about the rest, if I only look at that row, then everything will be very simple. Don't care, don't care. I get Sj, don't care, don't care, don't care. And so for this equation to be true, I need Sj to be 0. Similarly, S1 will be 0, Sk will be 0, they'll all be 0, and hence is a this is linearly independent, and so it is a basis for S. All right, so this is specific to this type of example where the vectors, the generators that you get come from solving a system. They have specific characteristics that make them linearly independent. If I give you a span with random generators, you have no reason to expect that they're linearly independent. All right, so here's a takeaway. When using the method of chapter 3 to solve a homogeneous system, you get x is S1 W1 plus SK WK. The vectors W1 to WK are automatically linearly independent. And so B, which is W1 to WK, is a basis for the solution set. All right, so that's it for this chapter.